Hey everybody, my name is Calvin and welcome back to my channel. Today we're going to be covering episode 13 of my Learn Python series. In the previous episode, we covered inheritance in object-oriented programming. In this episode today, I'm going to cover a couple more concepts, called encapsulation and abstraction. These are two object-oriented programming concepts that affect how a class manages its data, and how the rest of a program will use that class. What does encapsulation mean? Encapsulation means placing an object's data and the rules for changing that data inside the same class. Some attributes can be public and changed directly without causing a problem. Other attributes need to follow rules. In those cases, the class can provide methods that control how that value changes. Abstraction means providing a clear operation without requiring the caller to manage every step inside that operation. A method can combine several smaller actions into just one useful command. Start will create our lesson 13 folder like before, and we'll create file called 13-1.py. Here, we're going to be just using a simple bank account example for this entire lesson. Let's start out with a skeleton. We'll define a class called bank account, and we'll have our init constructor here that will take an argument self, owner, and balance. We want to define who the owner is and the starting balance. And we'll set self.owner equal to owner, set the attribute balance is equal to balance. And let's make sure that our class works. Create bank account owner self with a starting value of 500. Then we can starting balance. Count balance. Run this and we see starting balance 500. The class here stores the owner and balance as normal public attributes. We've already used public attributes throughout the previous object-oriented programming lessons. Here, the important part for this lesson is that any code with access to the account object can replace the balance directly. What we can do here now is set our account balance equal to -1000. And then we can print our updated balance, and we should see -1000, see -500 and -1000. Here, there is no method that was involved in that assignment. The bank account class has no opportunity to check the new value or reject it. Python simply replaced the original balance with our updated value, -1000. For this example here, let's assume that the account should not be allowed to have a negative balance. Public attributes are not automatically bad. A class can use public attributes when direct access is reasonable here. The problem here is that the balance has rules attached to it in this case. We can't have a negative balance. Deposits should increase the balance, and withdrawals should only succeed when enough is available. We could, theoretically, place an if statement everywhere where the balance changes, but then the account rules would be spread throughout the entire program. Every part of the program would need to remember how a valid deposit or withdrawal works. A better design, then, is to put those rules inside the bank account class. The object will store the balance, and the class provides the valid ways that we can change it. And that's going to be the encapsulation we're going to add next. The first change that we're going to do here is change how the account stores the balance. We'll change our attribute to start with an underscore. The leading underscore here is a Python naming convention. It communicates that underscore balance is intended to be managed within the class. Underscore here doesn't make the attribute completely private in this scenario. Python would still allow someone to access account._balance directly. Underscore here then in Python tells someone using the class that they should use the class's public interface instead. This is a bit unlike other languages like Java or C. Python doesn't completely block access to underscore balance. Someone could still write something like account dot underscore balance or assign a different value to it. The underscore tells someone using the class that they should avoid doing so and use the public operations that will be provided by that class. And that's how encapsulation is commonly handled in Python. Python generally relies on clear class design and naming conventions rather than strict public and private access rules that you might find in languages like Java. Here, we're also going to be adding a check before storing the starting balance. We'll do something like if balance is less than 0, meaning it's an invalid balance, then we set balance equal to 0. This prevents the object from beginning with a negative balance. Encapsulation applies when the object is created, as well as when it's changed later. If the class accepted an invalid starting balance, the account could begin in an invalid state before any methods were ever called. After the check, the validated value is now stored in underscore balance. We'll also add a property. The add property decorator allows this method to be accessed using attribute syntax. And then here, it's just a simple get method, balance. A normal method is called using parentheses. For example, you might write something like account.deposit parentheses 200 parentheses. A property here is accessed without parentheses. We can just write account.balance. Python will still run the balance method. That method returns the internal underscore balance value. This class now has an internal name and a public name for the balance. Outside of the class, the balance is now going to be read through the balance property. Let's demonstrate that. We'll adjust our print statement from before. We have a different print statement. We still have account.balance. Now, this will call on this property right here. And we can run the file, and we can see that we get 500. And what's the point of this? Now, if we wanted to assign account.balance outside of the property, this is not going to be possible. That's the point of that. A property can have a getter and a setter. The getter here defines what happens when the value is read. For example, our property method here only returns self.balance. You can't go ahead and change the balance without using this property anymore. We can see that when we try to set account.balance is equal to 1000, we get an attribute error, and that's intentional. I don't want the account balance replaced through direct assignment. I want the class to provide specific operations that control how the balance changes. And that property gives the rest of the program a simple way to read the balance while the internal value remains managed by the class. Let's add a couple more methods into the bank account class. We'll define deposit, which will take self and amount, and it'll perform a check for us. If amount is less than or equal to 0, then we want to print an error statement, deposit amount must be greater than 0, and we should return false. And we'll update our balance if not true. And we'll also add a corresponding withdraw method. Taking the same parameters, and we'll also check the amount that we're withdrawing. Amount is less than or equal to 0, then the statement like before. False. And if the amount is greater than self.balance, which is our withdrawal check, we print insufficient funds. False. If both of these checks pass, and then and only then can we actually withdraw the amount. We'll turn true. What did we do here? The deposit method gives the class a controlled way to add money now. The amount must be greater than 0. If the amount is 0 or negative, the method will print a message and return false. The return statement ends the method before underscore balance is changed. and that means invalid values never reach the balance update. The important design change here is that the code outside the class does not calculate a new balance and assign it. It requests a deposit. And going forward, we can increment our bank account balance by doing something like this. And here, we should be able to see that our balance is 700. The withdraw method follows a very similar structure, but it has two rules instead of one. Amount must be greater than 0, and the account must contain enough money to complete the withdrawal. Our bank account class here now contains the balance and the rules for changing the balance, and outside code does not need to repeat those rules. Now we can do count, withdraw, 100, and we'll try to draw more money than we have, then we can balance here. See our final balance after these transactions have gone through. What should we expect here? We start with a starting balance of 500, deposit 200, which gives us 700. We withdraw 500, giving us a balance of 200, and then we try to withdraw 700. That's not going to work though. We print insufficient funds. Balance of 200 and final balance of 200. And that's the main encapsulation example for the lesson. The balance is stored internally, exposed through a property, and changed through methods that enforce the account rules. Owner remains a normal public attribute because there are no special rules connected to this in this example. Encapsulation does not require our attribute to become internal, and is most useful when the class needs to protect the consistency of a particular value. The account now can process deposits and withdrawals. Now I'm going to use those methods to create one larger operation. Let's add another method called transfer to. We'll take in self, other account, and an amount to transfer. If not, self.draw amount. If we're not able to withdraw anything, we return false. And if our checks pass, then we can deposit our amount. True. To test this, we can create two new accounts. We can create a checking account, bank account object with me, and a starting value of 500. And we'll also create a very similar one, savings account, instead we'll have this start at 200, and then instead we'll have this start at 200. Print statements, transfer, our checking balance, checking balance, and we'll also check our savings account. And here we'll use our transfer to method to transfer $200 from our checking to our savings account. To checking account, transfer to savings account, and here we'll check it again. Let's run this completed program. And here we can see that our transfer successfully completed. We've successfully decremented 200 from our checking balance and incremented our savings balance by 200. Notice that without this method, the caller would need to coordinate the two operations itself. We'd have to have something like if checking.withdraw, then savings.deposit. And that's manageable in a small program, but it places responsibility for the transfer process outside of the class. If several sections of a program perform transfers, the same sequence could be repeated in multiple places. And that's the abstraction in this example. The caller requests a transfer, and the class handles the withdrawal, the failure check, and the deposit now. Our final bank account class demonstrates both concepts. Encapsulation is shown by the internal underscore balance attribute, the read-only balance property, and the deposit and withdrawal methods. Abstraction here is shown by the transfer method. The caller uses one clear operation instead of multiple. The class handles the smaller steps needed to complete that operation. Encapsulation keeps an object's states and its rules together, and abstraction gives the rest of the program a simpler way to use that object. And that's the crash course in encapsulation and abstraction. It's a very important concept that you'll need for object-oriented programming. It may not be as essential for use in Python, but it'll help you immensely if you ever decide to work with languages like Java or C. As usual, let's stage our changes, which is git add less than 13. We'll write a commit message, lesson 13, encapsulation and abstraction, and then we'll push this. I'm here. Push our repository. Thanks for watching, and I'll see you guys in the next lesson.